Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's Design News webinar, Optimized Interconnect Solutions for Design Flexibility in Portable Devices, sponsored by Highland Electronics and JAE, and broadcast by UBM. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar via social media outlets, and participate in our Q&A session that takes place at the end of our presentation. You can submit questions at any time by typing your question into the Q&A text area and then clicking the Submit button. Please note that we'll try to get to as many questions as we can at the time that we have left at the end of today's program. However, if we don't get to your question today, someone will get back to you after the program is over. And the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the Resources widget at the bottom of your screen. And towards the end of our webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a moment to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click on the Help widget found at the bottom of your screen or type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now on to the presentation, Optimized Interconnect Solutions for Design Flexibility in Portable Devices. Highland Electronics is a globally franchised distributor of interconnect, electromechanical, and sensor products, and is authorized to sell JAE's product portfolio of interconnects. Discussing today's topic is Kenta Minejima. Kenta Minejima is the marketing manager at JAE Electronics, where he manages research and development of consumer and mobile device markets. Kenta graduated from the University of California, Santa Barbara with a degree in electrical engineering and has over 10 years of experience in the electronic connector industry, focusing on a variety of different market segments, including transportation, data center, and medical. To learn more about today's speaker, please visit the BIOS widget. It's with great pleasure I now turn this special session over to Kenta to begin. Kenta, take it away.
All right, thank you very much, Chris. So first off, I want to start off with a quick overview of the agenda for today's webinar. So obviously, the kind of new industry standard for I/O interconnects with a lot of flexibility is going to be the USB TypeC interface. So first, I'm going to go over basically and do an overview of the actual standard itself, what it is, what kind of solutions it provides. And then I'll also go over kind of the electrical or high performance, high speed or power type of capabilities of USB Type-C, and also go into the mechanical design review. So there's actually a lot of changes and a lot of unique features that are built into the USB Type-C connector that's quite a bit different from all the traditional interface connectors, and also kind of go over some variations and things to watch out for when trying to incorporate or design in the USB Type-C type connector. And then also to kind of add on to the kind of new flexibility and advantages of the Type-C, there are a new family of internal connectors that help to transmit the same type of power and signals inside of your device as well. So first off, obviously we're going to start off with the USB Type-C interconnect overview. The design targets and goals when the USB Type-C specification was being created was to basically have a single standard USB interface connector that can connect all devices. That means that there would be no more need for different Type A and separate Type B type connectors for the host and peripheral. In past devices, you had to have a different shaped connector used at each end of the cable, which was one side would plug into the host device, such as a computer, and then the other end would plug into your peripheral device, such as a smartphone, camera, or other type of device. The cables obviously would only work in one direction, and the Type A and Type B connectors did have mechanical keys, so as long as you look at the connector or try to plug it in once, you can determine which end is supposed to plug in to which device. There should also be no more requirements for standard mini or micro size connectors based on the size of your actual device. In the past, as an example, a large printer at your office might have had a full-size Type B connector, whereas your smaller smartphone type device might have required a micro USB connector. That meant that you needed to have a separate or different type of cable depending on what device you're actually trying to connect. So even if your host side is always a standard Type A connector, if you're plugging in a smartphone versus a larger printer, you had to have a different cable for each, to connect each type of device. Also, with the introduction of the USB 3.0 standard, the cables were no longer backwards compatible at that point. Basically, the actual plug connector shape changed in order to add in these super speed pins that were required for USB 3.0. So that means that you could no longer use a 3.0 cable and plug it into slower or legacy type USB devices anymore. So again, the requirement to have a bunch of different types of cables for each user. With the new USB Type-C connector, all future devices can potentially be connected using the same basic cable without worrying about compatibility or the direction of the cables being plugged in. There was also a requirement to make the interface scalable to meet expected future requirements, including both bandwidth and kind of new features and functions that might be necessary in the future. The USB IF did not want to have, obviously, to have a connector that would be outdated and would have to be redesigned again after the next generation boost in speed or a new type of functions or features that were required by normal consumers in the future. And so USB Type-C obviously supports a very wide variety of signal types, signal speeds, as well as power levels. The first and obvious requirement is to be able to support USB signals since it is a USB standard connector. It does support up to the newest USB specification, which is USB 3.2. And that means that it can support a total of 20 gigabit bandwidth over 2 lanes of super speed pairs. The previous generation USB 3.1 specifications supported a maximum of 10 gigabit per second data over a single single lane. This was what people refer to as USB 3.1 Gen 2, and then USB 3.1 Gen 1 is actually supporting 5 gigabit per second. So USB 3.1 Gen 1 is equivalent to what previously was the USB 3.0 specification. The much slower USB 2.0 and 1.1 signals are also obviously supported in the USB Type-C connector. These original D plus and D minus data pair contacts still exist inside of the USB Type-C, so it can support all these previous generations from slow speed all the way up to the latest super speed plus data rates. Also, a brand new capability that the Type-C made possible was the capability to support what's being called alternate modes. So alternate modes actually allow the same USB Type-C connector to transmit other types of signals, either in addition to USB, so along with USB and other type of signals, or actually instead of USB. So instead of sending USB signals, it would be strictly whatever this alternate mode signaling was. Just some examples of what these alternate modes could potentially be. DisplayPort is a very commonly used alternate mode. Typically, you can see up to 2 lanes of DisplayPort being transmitted at the same time as USB 3.1, 5 gigabit or 10 gigabit data being transmitted inside the connector. Obviously, this is very ideal for docking devices. So if you want to have data to connect to other peripherals, as well as connecting monitors, TVs, or displays to your device. Obviously, having data and video in one connector is very advantageous. Another new standard that's adopting USB Type-C as the interface is called a virtual link. And a virtual link is actually a brand new standard for virtual reality headsets. And it's actually meant to support 4 lanes of DisplayPort plus USB 3.1 simultaneously. So obviously, the 4-lane DisplayPort is important for virtual reality headsets because they require even higher resolution, and they also have multiple displays inside the headset at the same time. So the lane count is for video is required for virtual link. So there is some special reassignment of pins that is a little bit different from standard DisplayPort alternate mode. Thunderbolt is also another new standard that's becoming more and more popular for personal computers. Basically, Thunderbolt combines PCI Express signals and DisplayPort video signals into one, muxes those 2 signals and sends it through the standard USB Type-C connector, starting from the Thunderbolt 3 revision. So previous revisions of Thunderbolt, Thunderbolt version 1 and 2, we're actually using a different type of connector, but starting from revision number 3, TypeC is the standard interface for that standard as well. In the future, there's obviously tons of potential for other types of alternate modes to be introduced that can also be supported using the standard TypeC interface. So that's very exciting to see. Another big key feature, in addition to all these neat new signaling features, is the capability to support a lot of power. The amount of power that can be sent through the connector and cable increased obviously significantly, and in large part that is due to the release of the USB PD, or power delivery specification. Obviously, initially USB was a standard that didn't really need to support a lot of power. It was only supporting a lot of PC peripherals such as mice and keyboards, and those devices didn't require a lot of power to operate. However, over time, USB has kind of started to become the industry standard for charging smaller devices, and so the power output through the USB connectors has started to go up over time through new revisions of the USB specification. With TypeC, it's now possible to quickly charge devices that have batteries, as well as devices that are actually not battery powered and have to be permanently plugged in to the wall outlets. However, one thing it is important to note that USB obviously is a DC power supply only. So for some of those devices that have internally integrated AC-DC conversion, TypeC cannot be the cable for that. You'd have to have a power brick or a wall adapter that changes to DC external to the actual device. As you can see in this table that's on the bottom of the slide, previous iterations of the USB specification only allowed up to a maximum of 7.5 watts, and so that was the USB battery charge, or USB-BC specification. There are kind of custom OEM-specific charging schemes that can support 10 watts or somewhere in that range as well, even kind of existing outside of the USB specification. However, starting with USB Type-C, even without USB power delivery or any special increased power, 15 watts is what basically any USB Type-C cable and connector can support. With the addition of the USB power delivery functionality, it's possible to increase that power output up to 100 watts of power. Obviously, that's a lot of power for, let's say, headphones or a smartphone, but when you're looking at larger devices such as laptops or trying to power an actual display or monitor, that type of 100-watt type of power comes into play. USB PD supports new voltage levels, and that's what kind of allows the power output to increase. And it's important that the voltages are increased rather than the current being increased too significantly, because the current obviously requires larger conductors to carry the increased current. A great advantage of adopting USB Type-C as a charging is that the charging adapters and cables can be shared among many devices regardless of power requirements. So due to backwards compatibility, it's possible to draw on the extremely large existing ecosystem of USB compatible peripherals and chargers. So that just means that if you have your typical USB charger for your laptop, the same charger could be used to charge your smartphones and headphones and possibly power up other types of electronic devices as well. So there's no need to carry around different types of power adapters based on the size of your device. Even with the USB Type-C connector, the power level will return to default USB power if higher power is not necessary for that specific application, or if it is determined that one of the devices that's connected is a legacy port. So default USB would mean the 1.5 or less current supply. USB PD also has a neat feature where it also allows for role reversal or reversal of power direction. So in the old USB, it always went from your source, the Type A side, to the sink Type B side. Whereas with USB PD, power can be going in either direction, and also you can change the direction of power even after the connectors are mated. In order to take advantage of the higher power capabilities, though, it is necessary to add a USB PD controller, which handles the communication and negotiation required to determine what voltage level and what current level to use. And so a lot of these features that we've just discussed, it's obviously a benefit to be able to support all these functions. However, there are a lot of potential areas of confusion that we've seen already. USB Type-C, first off, is a separate specification and document that covers USB Type-C connectors and cables only. Even though there's a lot of references throughout the Type-C specification to other specs, such as USB 3.1 and USB power delivery, they're actually completely separate documents. The fact that the release timing was fairly similar for USB 3.1, USB Type-C, and USB power delivery, they all came out basically or became mainstream at the same time, kind of makes it easier to get confused. And so actually the USB PD specification at the time of the Type-C release was actually already onto revision 3.0. So they were actually technically USB PD capable devices even before Type-C was invented or was released. However, PD was not really a very popular standard due to kind of special requirements of legacy connectors. But revision 3.0 is what came out at the same time as Type-C, and obviously that's kind of what's in devices now. The use of USB Type-C connectors and cables, so therefore it doesn't infer necessarily that either high speed or high power is actually being used. So USB Type-C connectors and cables can be used just for low speed charging and also for low speed data transfer as well. So it's not necessarily have to be USB 3.1 high speed or USB PD, high voltage, high current charging. Obviously this can cause confusion among implementers as well as consumers, and customers may not understand if they buy a lower spec cable, why their device is charging slowly or why their device is not sending data as quickly as they expect. In order to make it possible to identify the device performance, there are different USB logos and markings that were created to kind of advertise the capability of the cable and the device. However, obviously that's not always the case. In some cases, the OEMs might leave off the logo to put their own branding or own logo on the device. You can see at the bottom of the slide, there's a couple of visuals. These are kind of embossed logos that you'll find on cable assemblies. Just to go over some of the differences, the SS is what stands for the super speed communication. So if there's an SS by itself, that means that it can support at least USB 3.1 Gen 1 or USB 3.0. That's that 5 gigabit per second data rate. If you have that additional 10 in the top right corner of the logo, that means that it can do USB 3.1 Gen 2, which is that 10 gigabit per second data transmission. And also on the logo on the left side, you can see that the entire USB logo is kind of enclosed in what looks like a battery shape, kind of like a AA battery shape, and so that actually indicates that the cable itself can support 5 amp, so even higher current than the normal USB Type-C cables. Due to all these different type of capabilities that are built into the Type-C connector, there's going to be a lot of different cable variations in the market. Here's just a quick list of some of the variations that are listed in the USB Type-C specification. Notice that the USB connector could be different on either end of one end of the cable. There are different levels of signal speed, and there's also different levels for the max current level. Type-C to Type-C cables that support USB 3.1 will have to have at least 22 of the contacts terminated inside the cable. And those ones are going to be called, most people are going to refer to those as full-featured cables. And those ones can support higher speed USB signals and most of the standard alternate modes as well. The cables which have legacy connectors on one end or only support slower speeds have much fewer pins that are actually terminated. Obviously, if you remember to the old original USB Type-A style connectors, They only have 4 pins, and even the versions that support the higher USB 3.0 or 3.1 data rate, they only have 9 pins. So obviously the USB Type-C comes loaded with 24 pins, but you don't need all those 24 pins to support some of the legacy USB signaling. One new thing that was introduced with the USB Type-C specification is a ID chip, which is required to identify the cable's performance or capabilities. This ID chip is typically referred to as the E-marker or electronic marker, and it stores information almost like basically like an EEPROM. It stores information about the signal speed capability, how much power or current the cable can support, as well as you can put in vendor-specific information such as lock codes or manufacturer ID and other type of custom information that you want to load onto the cable itself. All the C-to-C cables that can carry 5 amp of power or support USB 3.1 must have E-markers built into the cable itself. E-markers are optional for other USB 3.1 legacy cables. The cable types with the legacy USB connector on one end use basically simple pull-up or pull-down resistor terminations to help identify the cable orientation. The pull-up or pull-down resistors help the devices identify which pins on the Type-C connectors are active, and then also how much power is available to be transmitted. Even though most of these legacy cables are capable of 3 amp current, all the devices should be operating at the default USB power levels, which are well below 3 amps. Early on, there was kind of a lot of news about devices that were overheating or being permanently damaged because they were being plugged into non-compliant plugs, because some of these pull-up and pull-down resistors were not implemented correctly. And so there was some kind of initial confusion with that, but at this point, people have kind of become more aware of the spec, and most of the cables out in the market right now should have the proper pull-up and pull-down resistors that identify how much current the device can actually pull. So for testing and certification, kind of to guarantee the performance of the actual cables and connectors, USB, as has been the case for previous generations as well, there's approved third-party test labs that do mechanical and some electrical testing to ensure basically that the products, whether it be the connector, cables, or the actual device itself, make sure that those are all meet the USB requirements, and also helps to guarantee that they're going to be connectors are going to be intermatable and operate properly when connected to other vendors' devices. There's basically no connector high-speed certification testing available. There are recommended high-speed performance benchmarks. However, those are all informative specifications. So basically, when you submit these connectors to certification testing, the high-speed signal integrity testing is actually not conducted. Cable assemblies, on the other hand, do all have to go through signal integrity testing, as well as power certification. Both connectors and cables do go through basic mechanical testing, such as contact resistance, temperature cycling, mating durability, and retention force. The cable side also has some additional kind of cable flexing, wrenching torque force type of testing as well, which is somewhat new. USB Type-C also now uses new calculation methods to validate signal integrity performance rather than your traditional kind of insertion loss, return loss, or crosstalk plots. There's fitted functions and integrated parameters that are used to help define whether a cable can pass or fail on the specification. The main reason for kind of using these new integrated parameters is basically to avoid rejecting cables that will actually function properly in the real world, but maybe have a spike at a specific frequency and might fail the traditional S-parameter testing. Some alternate modes, it's important to note, do require additional testing outside of what USB does. So, for example, Thunderbolt 3 and Virtual Link are examples of two standards that actually require USB Type-C certification as the baseline, and then they actually have additional testing requirements just due to either the bandwidth or the way that they assign high-speed signals inside the connector. They actually have additional or more strict signal integrity requirements. So it's important to understand that that's required in order to certify a specific device for those alternate modes. And here we kind of start to go into a mechanical overview of the actual connector itself. You can obviously see by looking at this pin layout that it is a symmetrical pin design. The V-bus and the power and the ground pins obviously are located in positions where even if you rotate the connector, they will be in the same place. You can also see the 4 super speed pairs that are in blue, and basically the increase in number of pairs is required to support many of these alternate modes that require video transmission, since a lot of those video transmission standards do require 4 high-speed pairs. In the normal USB operation, only the D plus, D minus pins and one set of the super speed transmit and receive pairs is actually used. Like mentioned earlier, a lot of times inside of a cable, not all of these pins will actually be terminated. In order to allow for hot plugging, same as previous generations of Type-C, the power, the V-bus, and the ground pins are made a little bit longer so that those are the first to mate. And again, to allow for the hot plugging without having to shut down your device. The new pin, the CC or configuration channel pin, is kind of the key new pin that allows for a lot of the new functions to operate properly. It's used as a communication line where the 2 devices can communicate to negotiate power or which side is the host and which side is the peripheral. And also the E-markers, the cables that have the E-markers embedded, the CC pin is actually connected to the E-marker directly to read the information about the cable. As previously discussed, USB PD communication is also done over the CC pin, so the kind of bidirectional power negotiation and things like that, and the power level negotiation also occurs over these new configuration channel lines. Also, kind of opposite of the configuration channel pin on the plug side is going to be a new VCON pin. So basically, it's another power pin that's separate from the normal V-bus pins, and this one is specifically integrated or added into the connector to support active components that live inside the cable. So that could be anything from redrivers, or it could possibly potentially in the future be optical transceivers, and also even the E-markers inside the cables. They can pull power from this VCON pin to power the actual chip and to activate the actual chips inside the cable. And also there's going to be 2 SBU or sideband use pins. Those are kind of unassigned pins in normal USB operation, but in alternate modes, those sideband pins can be used for different functions to support whatever the requirement is for that specific alternate mode. And kind of a mechanical comparison, it's kind of hard to tell, but USB Type-C is actually a little bit bigger than what became the standard for kind of compact portable devices, the micro USB connector, but it is still significantly smaller than your traditional ports that you'll find on a laptop computer, like your mini display port, USB Type A connectors, and also the HDMI style connectors. So you can see that there is kind of a deficit or a penalty to pay for having to support so many features and functions. The connector had to include 24 pins, whereas an equivalent USB micro USB 2.0 connector only had 5 pins inside. So it is very difficult, obviously, or basically impossible to keep the connector at that size. The contact spacing, one of the things that was changed, the contact spacing in the USB Type-C is a little bit less than some of the other standards. So right now it's at 0.5 millimeter spacing between pins. However, that smaller pitch is not too much of a concern. Other standards exist that use 0.4 millimeter or 0.4 millimeter spacing between contacts. So 0.5 is not necessarily a concern for mounting and soldering in most devices. There's also a lot of new mechanical features that are integrated in the TypeC connector. So there was actually a significant struggle and a lot of effort put into making the connector design as small as it actually is. The final design ended up being, and it's still a small enough connector to be a good fit for portable and compact electronic devices. So moving on to some of the actual features, and so these are all kind of basic standard features that you'll find across all USB Type-C connectors, regardless of the actual vendor. Kind of the main mechanical feature that USB Type-C is known for is having the reversible structure so that the plug can be inserted in either orientation. Of course, this helps to provide much better user experience since there's less frustration when trying to make the connectors. If you're accidentally trying to make the connector upside down, obviously the connectors won't mate properly. However, also from a manufacturing standpoint and design standpoint, this actually really helps to minimize the risk of damaging the connector when the user does do that, try to make the connector upside down. The keying features and the internal tongue inside the connector where all the contacts exist was typically the weak point inside of connectors such as micro USB, and that the internal tongue where all the contacts are located is very thin and typically very easy to get damaged if the plug is inserted upside down or at an angle. Obviously, this reversible capability kind of provides a good user experience, but also kind of automatically improves the connector reliability as well. Another brand new feature that's unique to the USB Type-C connectors is a unique ground structure. It actually has special ground springs that are built into the inside of the plug connector. The ground springs are offset and isolated from the normal signal pins inside, as you can see in this kind of cutaway view of the plug connector. Ground springs are located in a position to guarantee that they will not short to the V-bus pins in the receptacle during insertion. So obviously kind of having offset or overlapping contacts, ground and power contacts might be a concern, but there is consideration taken in the design to make sure that can't happen. The mating receptacle connector will typically have ground plates on the top and the bottom, kind of in the back end of the connector. And this ground plate is basically where the ground springs from the plug side would make the connection. Another option for grounding, if you do not want to have ground plates inside the receptacle, is to cut out spring fingers out of the receptacle shell, as you can see in the example of the connector at the bottom right. Basically, you can cut out spring fingers out of the connector shell to create at a minimum of 4 ground contact points inside the connector. Basically, this is a hard requirement of the USB Type-C specification, so there has to be at least a minimum of 4 ground connection points between the plug and receptacle shell. So that's a good point that all compliant Type-C connectors are going to have good EMC control. Another thing to note is that that's fairly consistent inside of new I/O connectors is the fact that all the spring contacts are located inside the plug connector instead of the receptacle connector. Basically, the main reason for that is that the spring contacts obviously are the side that moves and the side that's more likely to fail. So obviously, the plug side is typically the cheaper device, so it'll be an accessory cable. Whereas the device, actual host device, obviously is probably going to be the more expensive side, so you don't want that side to have any failures. A couple of other neat new features that are added in with the USB Type-C is actually a new mid plate. It's actually a stainless steel, typically a stainless steel plate that runs inside the connector tongue in between the 2 rows of contacts. In all USB Type-C connectors, this mid plate must be tied to the common ground, and that allows this to be used as a ground plane, and it helps to control differential impedance, obviously, by controlling the distance and the thickness, as well as it helps to give isolation in between the top and bottom row of contacts to reduce crosstalk as well. The size and the shape of the mid plate does vary from vendor to vendor, so it is important to understand kind of how your specific connector that you've selected is actually designed internally. Obviously, that mid plate also provides mechanical rigidity to that entire connector tongue area as well. Another mechanical feature which is internally integrated in the TypeC connector is the friction latch now. The latching feature in all other I/O connectors typically requires holes, again, and springs to be cut out of the plug and receptacle shell. The TypeC plug has, again, these components integrated inside of the connector, which helps to avoid having to cut these holes out of the outer shell, which leaves a kind of very aesthetically pleasing and very good-looking plug connector with just a kind of a flat shell running all the way around the outside of the connector. These connectors are rated for 10,000 mating cycles, which is the same as the old micro USB specification. In the area where the actual friction latch engages, you can see that the mid plate in the receptacle tongue is actually exposed outside of the plastic. And the reason for that is to improve the longevity. It's very important to have this metal-on-metal contact, so the metal spring latch in the plug makes contact with the metal mid plate inside the receptacle side. So basically, obviously, having metal on plastic over time is going to wear out the plastic very quickly, and then it's going to reduce the effectiveness of the locking latch and reduce kind of the retention force of the connectors. This internal latching feature also actually gives a good ground path inside the connector as well. So kind of a warning or problem area that I've seen a lot in a lot of new implementations of the connector. The connector mating depth is kind of an important feature that's no longer controlled in the USB specification. In previous specifications, basically the connector cell length was fixed by the specification, and everybody had to follow that. Whereas with the new USB Type-C, it's actually flexible. So the connector mating depth, typically for most connectors that you'll find on the market, are going to be in that 4.5 to 5.5 millimeter range. The actual total mating depth that's recommended by the USB specification is 6.2 millimeters. So that just means that in most applications, it's expected that the standard connector will kind of be recessed off the outside of the device enclosure, and so that'll help kind of make up that extra mating depth, which adds up to the total 6.2 millimeters. And the main reason for kind of having this flexibility where you can adjust this mating depth or shell length is to allow for different shaped devices. So if you wanted to have kind of a angled cut of the outer enclosure, or have a curved device that had a very, very large radius, being able to have this connector with a very, very short shell, a short mating depth, allows you to kind of modify the enclosure design freely without having to modify the connector itself. So you'll see a lot of different connectors that are even well below 4.5 millimeter mating depth, and you'll also see some connectors out there that are at the full 6.2 millimeter mating depth. And where this kind of comes into or becomes very important is that obviously if you have the full 6.2 millimeter depth inside the connector itself, you have to make sure that that is mounted flush to the outside of your enclosure. If it's recessed too far back inside the device, the actual the overmold of the plug or the hood of the plug actually will run into or butt up against the outside of your device and not allow the connector to fully engage. So it's kind of very important to keep that in mind when implementing USB Type-C connectors, to kind of keep an eye on what the actual connector mating depth is. Just a few other standard features that have been kind of common from before is different type of mounting heights, obviously depending on the shape and size of your device. Sometimes you want a taller connector, sometimes you want a shorter connector. Also, vertical mount connectors obviously are already available. And one thing to note, no more requirements obviously for reverse mount connectors. Since this is a completely symmetrical connector, previous I/Os such as USB, there was typically a reverse or a top mount type depending on which side of the board the connector was actually mounted on. And another feature that's unique to USB Type-C is that it actually has obviously 2 rows of contacts to make to improve the connector density. And so you can see that these 2 rows of contacts basically come back down to the board and there's 2 rows of contacts on the PCB mounting area as well. So there's kind of 2 main types of connectors. One is going to be where both rows of contacts are going to be surface mount. The concern there would be that basically you can't visually inspect and you cannot rework that inner or bottom row of contacts because it's basically hidden underneath the connector. The alternative to that is what we call hybrid style contacts, where the outer or top row of contacts would be surface mount still, but the inner or bottom row of contacts is actually through-hole pins. So one advantage that that has potentially is that the through-hole pins, obviously you can see from the bottom side of the board, and so it's possible to do some reworking in most cases. However, typically for kind of high signal integrity requirements, the surface mount contacts are typically perform a little bit better than through-hole contacts. However, again, through-hole contacts does give a little bit possibility for reworking. In terms of board retention, hold down and things like that, the hybrid type versus a dual surface mount type, there really isn't too much of a difference. It's more or less the placement of the large shell hold down pins that makes a difference for the actual shell retention. And here's just a list quickly of some of the variations that even that just JAE has. So you'll see a lot of variations from a lot of different vendors, for all the new features that we've gone over, connector style, mounting height, shell depth, mating depth, as well as new features such as waterproofing and things like that. So there is a lot of options available, but just make sure to kind of keep note of a lot of these kind of unique features from each connector, since each connector or each vendor might have a lot of different designs. For the plug connector side, it is very common for the plugs that go inside the cable assemblies. They're actually mounted typically to a intermediate paddle board. Basically, that paddle board allows you to mount other components such as these pull-up and pull-down resistors, as well as active components or E-markers inside the cable itself. Also, it allows you to increase the contact spacing or the pad width. So you can see kind of on the back end of these paddle boards, you see the rectangular shaped pads, and so that's where you would be soldering the wires inside the cable to. So obviously, once you transition to a paddle board, it's possible to spread out the spacing between those pads to make it easier to solder larger wire sizes. Whereas if it was 0.5 millimeter contacts, the way the USB Type-C mating area is, it would be difficult to fit larger wire sizes directly into the back of the contacts. There also are top mount plug options for kind of docking and for other type of applications where the connector can be mounted and all contacts are on one side of the board. So that does help to speed up assembly process, but a lot of times it limits the kind of application based on whether the direction that the plug comes out for the vertical style or the number of pins that are possible to mount on only one side of the board for the top mount plug. So quickly, I want to go over some kind of internal connection options. Obviously, Type-C, like I mentioned, has so many features and capabilities, but the internal connection is also just as important in many cases. This is just one potential block diagram of the inside of a portable, battery-powered device that uses a USB Type-C port. Typically, it's very difficult to have all of your components, including the I/O port, mounted to the single main board side of the device. So that obviously there's a lot of, like we mentioned, a lot of height variations in USB Type-C that are available. However, to match every single specific case design, outer chassis design, and board placement is very, very difficult. Also, there's also going to be a lot of applications or instances where there's going to be other components, such as, let's say, a battery cell being placed right behind where the connector is mounted. That means that you're going to have some type of a cable connection from your Type-C I/O port back into your main board. And so using flexible printed circuits or FPC cables is actually a good solution. You can either mount the TypeC connector directly onto a FPC cable by applying a reinforcement stiffener in that area where you do the mounting, or you can also have a kind of a sub or daughter board for the rigid PCB where the connector is mounted once, and then you can use a jumper cable from that daughter board back to the main board. So there's a lot of these new compact FPC style connectors with a plug-in socket side, where the plug side mounted on the flex, a receptacle or socket side can be mounted on the main board side. And kind of the reason or the good feature about this new internal connector is the ability for it to carry both power and signal in one very, very small and compact package. So this is just an example of one type of connector, but there's other types that have similar type of electrical performance capabilities. So this is an example where there's a lot of small, low power signal contacts basically located inside the middle of the connector. So these pins will usually be rated for about 0.3 amps. So obviously you can't transmit a ton of power over these pins without ganging a lot of them together. But actually on the edges of each connector, there's actually power pins integrated into the hold down area. And so typically these hold downs are going to be able to support around 3 amps of power. And so obviously that matches up perfectly with the typical current supply of a USB Type-C, which is 3 amps as well. So this is an ideal connector to connect back from a USB Type-C connector back into your main board. It can support both the power, 3 amp power for fast charging, as well as the signals that need to run obviously through the USB Type-C. For battery charging, obviously the batteries operate at a much lower voltage than USB power delivery, so the current level actually has to go up. And so there's actually similarly designed connectors that can actually support even more power, up to 10 amps in some cases. And you can see in the picture in the bottom right kind of a comparison of a quarter versus a couple of these type of connectors. One of them on the left has 34 signal pins plus power, and then the connector placed on the right side of the quarter is an example of a battery type connector that can support actually 10 amps. You can see from that sometimes it's kind of hard to get a good idea of the scale or size of these connectors. You can see from that these are still very, very compact connectors that can be easily integrated or incorporated inside of compact or portable devices. And just to note, this basically the same style connector and connection method can be used to kind of modularize any other components inside your device. So let's say camera sensors or LED indicator lights, mechanical switches, and then the batteries, like we mentioned earlier. All these components can be kind of separated, made as a separate module, and then connected back into your main board using these new kind of flexible FPC connectors that can support a wide variety of signal count, as well as high power as well. So that's the end of the presentation, and I'm going to hand it back over to Chris.
All right, thank you, Kenta, for a great presentation. We're now going to move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen. And please note that we'll try to get to as many as we can here in the time that we have left. If we don't get to your question today, someone will get back to you after the program is over. And let's move on now with our first question for Kenta. Kenta, currently USB-C connectors are much more expensive than micro USB. Will there be a point when there may be a price parity from C to other styles?
Yeah, so that is absolutely true. Obviously, Type-C connectors are going to be probably maybe double or even more the price of a traditional micro USB connector, and that's just based strictly on the fact that it has so many more pins and is so much more difficult to manufacture. There are new types of products coming online shortly that are going to have some of the actual pins pulled out of the Type-C connector. So in cases where you only need power or you only need to support slow speed data transfer, you'll actually have a slightly less expensive connector with some of those pins pulled out. However, I don't see the Type-C connector ever being at the price point that micro USB was. Obviously, that was a very, very inexpensive connector just due to the size and the number of pins in it, and obviously the sheer volume. But the USB Type-C connector has seen a pretty significant, I'd say even from when it was first introduced maybe a couple of years ago, the price has pretty much, let's say, been cut more or less in half since it was first introduced already. So there will be continued kind of price decreases because it is obviously a commodity style item in many cases because of the high volume and the many different vendors that do actually manufacture the Type-C connector. But there is, I feel like there's basically going to be a little bit of a price difference always between Type-C and the kind of legacy micro USB style connectors, and that's kind of the payoff for the payoff is that obviously you can do a lot more things, and as Type-C kind of becomes more and more popular, it's probably going to become more important that Type-C is integrated in your product because there's going to be so many Type-C chargers and peripherals that are compatible with Type-C ports out there. So kind of being able to be a part of that huge ecosystem obviously is going to become very important.
All right, thank you, Kenta. Just as a reminder, to ask a question, just type your question into the Q&A text area, and then click the submit button. We'll get to as many as we can. Looks like we have just a couple more questions for you right now. So I'm encouraging our audience, if you do have a question, this would be your time to get it answered. So let's move on with our next question here for you, Kenta. How is the adoption rate of USB Type-C in the market?
So it's actually been accelerating very rapidly. Initially, the areas where Type-C was most commonly seen was in kind of high-end laptops that required kind of the higher speed or faster charging capability of Type-C, but then also in high-end smartphones. So the kind of top-of-the-line, top-tier smartphones would have Type-C kind of as a new feature, a selling feature for the kind of reversible connector and faster charging of devices. But over time, it's actually started to move into kind of mid-tier devices, both computers as well as laptops as well as smartphones. And also, it's also being used as a power supply only in many, many different types of devices, including things like even routers, USB memory devices, and things like that as well. So obviously, it's an extremely flexible connector. So there's a lot of new industries that are starting to adopt USB Type-C as a standard interface, regardless of whether it's for its power capabilities, just its flexibility in terms of being able to reverse mate, as well as kind of different types of data rates that it can support.
All right, thank you, Kenta. Another question that came in for you says, what's the USB signal speed being used most often in our current devices?
Yeah, so typically most devices actually only do support USB 2.0 speed, and a lot of them actually only support legacy USB power level, so that 1.5 amp or less. And obviously all the great new features that we just discussed today, it's kind of interesting that currently, in the initial stage at least, a lot of the devices out there actually don't take advantage yet, and more or less because there's not enough support of different types of chargers yet that can support the ultra high voltage and current levels for charging, and also there's not a lot of chipsets out there that can support 10 gigabit type of USB 3.1 data rates yet either. So as kind of time moves on, obviously signal rates are going to continue to go up. Batteries inside of electronics are going to continue to increase in capacity, and so more and more devices are going to want to have that faster charging and faster data rate capability inside of their devices. And again, as I mentioned, as more Type-C devices come out there, more accessories, more peripherals with Type-C on them are going to be coming out. And then we'll probably see a shift to, support for 5 gigabit and also for, 60 watt or 30 watt type of devices.
All right, well, thank you, Kenta. Those were some great questions. That looks like all the time that we do have for questions for today. I'd like to thank Kenta Minejima. Design News appreciates your time and your expertise on today's topic. And thank you to our sponsors, Highland Electronics and JAE, as well as everyone else in the audience. We appreciate your attention and participation. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been available to listen to today's event. This webinar is copyright 2018 by UBM. The presentation materials are owned by our Copyright by Design News and Highland Electronics and JAE, and the individual speaker is solely responsible for his content and opinions. On behalf of our guest, Kenta Minejima, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.